Hello and welcome to another episode of TWiML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. Before we dive in, a quick community update. The TWiML study group is at it again. For the next 4 weeks, starting May 25th, we'll be diving headfirst into Peter Abeel's Full Stack Deep Learning course. This course is a great complement to the Fast.ai courses we've done so far and covers practical topics like problem formulation, data acquisition and preparation, establishing the right frameworks, platforms, and compute infrastructure, debugging and ensuring reproducibility, and deploying and scaling your models. For more information or to register for this study group, visit twimlai.com/fullstack. I can't thank our volunteer study group hosts enough for all their hard work. A huge shout out to Michael, Christian, Kai, Sanyam, Joseph, Dinesh, and everyone else that's been involved in making this group happen. A hearty thanks to our friends at Qualcomm for sponsoring today's show. As you'll hear in the conversation with Max, Qualcomm has been actively involved in AI research for well over a decade, leading to advances in power-efficient, on-device AI, as well as in algorithms such as Bayesian deep learning, graph CNNs, gauge equivariant CNNs, and more. Of course, we know Qualcomm powers some of the latest and greatest Android devices with their Snapdragon chipset family. From this strong foundation in the mobile chipset space, Qualcomm now has the goal of scaling AI across devices and making AI ubiquitous. In this vein, a product I'm particularly looking forward to is their Cloud AI 100 line of data center inference chips, which I learned about at their recent press launch. To learn more about what Qualcomm is up to, including their AI research, platforms, and developer tools, visit twimlai.com/Qualcomm. All right, everyone, I am on the line with Max Welling. Max is a research chair in machine learning at the University of Amsterdam, as well as vice president of technologies at Qualcomm and a fellow at the Canadian Institute for Advanced Research, or CIFAR. Max, welcome to This Week in Machine Learning and AI.
Thank you very much, Sam.
It's great to get a chance to chat with you, Max. You're quite accomplished in the field of machine learning, and I'd love to understand what drew you to AI and how you kind of started your career in this area.
I actually started not in AI, I started in physics. So I did my PhD thesis in theoretical physics. And that was fun, but it was also somewhat abstract in the sense that I couldn't see how I could have a major impact with that. And so I decided I wanted to change to a field that was a bit more, less static and more dynamic at that point in time. And so I wanted to do something like neuroscience, which I thought was a great choice. And so I applied to Caltech, to Pietro Perona's lab. But I basically ended up doing computer vision there. And then later, when I went to London, I worked with Jeff Hinton. I was doing machine learning. So I sort of meandered, from physics through computer vision to machine learning. And there I really, found a home because I thought, okay, so this is going to grow big in the future, which actually happened. And there's so many applications with which, this field can impact the world in a positive way that I sort of decided to stay there.
That first jump into computer vision, was that computer vision applied to neuroscience in some way?
No, it was just computer vision, basically analyzing images on a computer screen, basically, right? So it didn't have anything to do with neuroscience. Although I was fascinated by that question, and I was going to some meetings on neuroscience, and integrated somewhat with neuroscience and Caltech. In the end, I was doing computer vision, which was great too.
Okay. And I get a chance to talk to a lot of folks that started their career in physics. A lot of folks more on the applied side, whether astronomy or dealing with things like some folks that work at using colliders and things like that, but you are more on the theoretical side.
That's right. Yes, I was doing my thesis in 2+1 dimensional quantum gravity, so it was very abstract and theoretical. It gave me a good, basis for mathematics, but it wasn't very applied. That's true.
And so at some point along the line, you started a company, Cipher. When was that in your career, and what was the inspiration for the company?
Yeah, so that was actually when I came back to the Netherlands. So I had my career was in North America and a little bit of time in London until about 6 years ago when I decided to come back to the Netherlands. And fairly quickly after that, we founded this company. It was it was an interesting story because we were working with a big Dutch bank, and they wanted to do a competition to predict what ads customers would want to click on when you offered them. And they were doing that with a bunch of big sort of consultancy companies. And I was asked to basically arbitrage, right, to make sure that everything went right and the competition was fair. And in order to do that, I just asked one of my master's students, Taco Cohen, who's also working at Qualcomm at this point, to also implement some models. And he did that on his laptop with a single GPU in it. And then when we looked at the results, we basically we beat all the big companies, and the big banks said, if that's the case, then you get the job. And so that was the start. That was the start of our company, right? I then two other people joined, Tijmen Blankenvoort and Jurgen Sandig. Jurgen Sandig was an old physics pal of mine, and that's what started the company. And from there, 5 good years of running. We did lots of consultancy with companies, and looked at their AI problems. And then Qualcomm came around and said, you have a good sized group here, all very experienced people, nice practical attitude. And they wanted to acquire us. And, there was a couple of other companies also that were looking at us. But, we went with Qualcomm.
And at the time Qualcomm came around, were you looking to be acquired, or were you ready to try something else? Or did it, did the opportunity just present itself and you evaluated it on its terms?
Yeah, we did the latter. So we weren't optimizing for being acquired or anything. It was just like, we were having a lot of fun, and some people actually thought, that we should keep going and grow. Other people thought, maybe it's actually interesting to join a big company and, have a lot more oomph, like a lot more power. You can make a bigger impact if you're part of a big company. And so it was basically an opportunity that we evaluated at that point, and we thought, well, this is good. We should try this.
But prior to, the primary focus of the company was on consulting. There wasn't a product being built or something along those lines?
Yeah, we did actually build a product as well. So there was an active learning tool, which was actually implemented at Tata Steel. And it works as follows. So you have an expert. So there was like cameras looking at slabs of steel which were being produced, and there was sometimes small little sort of defects on that steel. We had a battery of cameras above it, and we were detecting these defects. But there were a couple of classes, and some of these defect classes were very rare. We didn't have a lot of data on them, and so the algorithm didn't perform very well. And so then the algorithm assessed itself and said, okay, so for these types of images, we need more labels, and so that was then shipped to an expert. The expert would label it, it would go back into the system, and the system would learn again and become better gradually over time. So that's active learning, where there's a human in the loop and the algorithm interacts with the human. And that was basically our product.
Okay. I can't speak necessarily to the approach, but it sounds very similar, at least from a problem domain and general direction to lots of folks are going after this area, but Landing AI, Andrew Ng's company, comes to mind as kind of tackling that similar kind of applying AI to industrial problems, including like defect detection, things like that. Was that product kind of one of a portfolio of challenges that you were going after, or was that a big focus?
It wasn't a big focus, actually. So this company was more opportunistic in that sense. So we We basically talked to a lot of companies in a very diverse set of sectors. So from finance to manufacturing, to retail. And we basically, we were very good at going in and talking to these people and say, okay, what is your, what is your problem look like? Where's your opportunity? What data do you have? And then we did a quick assessment and we made a recommendation and perhaps a very quick demo. And then if they were happy, then we went for a slightly longer sort of trial where we would actually, implement, a system to just show them that, you can actually get value out of the data that they have. And if they were still, happy after that, and this was like maybe 6 months later, then we would go into an actual implementation of the whole thing. And so we repeated this many times with many companies, which gave the team an enormous amount of sort of experience with a very broad spectrum of problems. And I think that's what made the team also very attractive.
So that acquisition was in 2017. You're a couple of years in now at Qualcomm. This thesis of kind of the oomph of a larger company creating some opportunities for you, did that thesis bear out?
The interesting part of working for Qualcomm for me was that I have always taken compute for granted. Basically, if I needed to compute something, then there's this computer which has some chips in it, and it will do its job. But with the advance of deep learning, we see that bigger models just perform better, and so compute becomes a really important part of the equation. And so, a good way to make progress is to make sure that your algorithm actually runs extremely efficiently. And so, of course, the GPUs came and they made deep learning compute a lot more efficient, which is part of why things are going so well with deep learning. But this is a very fundamental question, right? It's like, okay, so a brain doesn't compute with 32 bits precision. It's very noisy. So should we change our compute paradigm in our computer as well? Should we maybe try to train with a lot less precision, maybe a couple of bits precision? Do these neural networks have to be so huge, right? These neural networks typically have like even hundreds of millions of parameters, sometimes billions of parameters. Do they necessarily have to be that big? Because that consumes a lot of memory and compute as well. And also, if you go a little deeper, if you dig a little deeper in the problem, then what you find is all these parameters of these big models, they are living in sort of off-chip memory called DDR, and you have to bring them to the registers where you do all the MAC computes, the multiply and accumulate computes. And that movement of data costs a lot of energy. And so, but in the brain, actually, it isn't so separated. We call that separation the von Neumann architecture, where memory and compute are very separated. But in a brain, actually, what you find is that the memory and the computer are very close, right? Because things are stored in these synapses between neurons, and the neurons compute, and so much more distributed. And so there's a lot of fundamental questions of can we just change the compute paradigm so that we can do things far more energy efficient. And that's basically what I find the biggest thrill of working in Qualcomm, in actually trying to make that happen, and then scaling up sort of AI computations a lot, which might actually be one of the big reasons why we're making a lot of progress. And then basically shipping whenever you have such a thing, and you build a chip on a new paradigm or a new principle, you can then put them in a chip and you can then ship them to a billion customers in a billion phones, right? And that's the scaling you were asking about, which is extremely exciting.
You've got joint appointments both with in academia and Qualcomm. That's becoming increasingly common, but everyone kind of manages it differently. What's the relationship for you? How is your work and research distributed across those appointments?
Yeah, so I have like about half an appointment in academia and half an appointment in Qualcomm at Qualcomm,
okay,
which I think is actually a very good distribution. So typically in the university, you work on more fundamental questions, which are very far out, and don't have a sort of a horizon of being productized or finding applications of 4 years maybe. So I'd say at Qualcomm we work on on problems which between 1 year and 4 years or 5 years will find an application within the company. In academia, you're completely free to do whatever you want, and it could be 100 years out if you wanted to.
Mm-hmm.
So it's interesting to have one leg in sort of both of these ecosystems and both of these environments.
It does strike me that some of the things that we're talking about here are coming up with fundamental new compute architectures, perhaps that are more inspired by the brain and synaptic and neural architectures, things like that. That could be very far-reaching research. Are you working on that kind of work in the academic setting as well?
So the compute. Sort of thinking about how compute interacts with, with AI and machine learning and intelligence. That's something that I exclusively do at Qualcomm. Although it did start in academia, so I was doing Bayesian deep learning. So Bayesian statistics is a particular paradigm, a statistical paradigm. So you have frequentist and Bayesian sort of statistics. In Bayesian statistics, you put probability distributions over your model. You basically say, I don't know, what my model really is. So I have some probability distribution over my possible parameters of my model. And then when I see data, I'm going to narrow down that distribution of parameters to the ones that are actually describing the data that I see. So that's something that wasn't really applied at deep learning. And so we started to apply that statistical paradigm to deep learning, which was a challenge because there's millions and millions of parameters that you have to sort of handle that way.
Mm-hmm.
But what we found is that we could use that paradigm to basically compress a neural network, with a factor of 100 without losing any of the accuracy, which was actually a big shock to me. Which is like, okay, so we're working with these models which have 1 million parameters, but you could train the same model. You could just keep 1 out of 100 parameters and throw away all the rest. And you would have a model which would function exactly the same way, which would not be any worse than the one that you started with. And so that's generally known as compression, neural network compression. So they are heavily over-parameterized.
Mm-hmm.
So, and we did that within the paradigm of Bayesian deep learning. It was a very good fundamental tool to do that compression.
Did you apply this compression to these Bayesian deep learning models, or is there something fundamental about Bayesian deep learning that allows it to, that's synergistic with this kind of compression?
Yeah, so it's more the latter. So
okay,
so it's basically, so you have a neural
because we
network.
do this kind of compression with traditional CNNs and the like as well, right?
Yes, that's right. So basically, it's one technique to do this compression on a neural network. It has some additional advantages, which is that you can also sort of express your uncertainty over a prediction, right? So you can actually say, I think it's this class, or this is happening in an image, but I'm 80% certain that that's actually correct, right? And so the Bayesian paradigm also allows you to do that. But you can also use it to prune large parts of your neural network away. So it's sort of a principal way of doing that. And so we started doing that, and that's coming back to academia versus Qualcomm. So we started doing that in academia because that was a very academic exercise at that point.
Mm-hmm.
But it became practical because we could compress these neural nets. And then we took it to Qualcomm, and now there's a whole team led by Tijmen Blankenvoort, who is basically trying all sorts of algorithms to try to compress these neural networks in the most practical way. And often the Bayesian way is not the most practical way. It could be perhaps like a very good way, but it's not yet a very hands-off way to do things. And so some of these other methods, which are much simpler to understand, can also compress these neural networks to basically the same degree. And those are the ones that actually make it into the toolkits that we use at Qualcomm.
It sounds like there's kind of a dynamic relationship, I guess, as one would expect between the kind of things you're working on from an academic perspective and what you're doing at Qualcomm, although, they differ in their time frames.
Yeah, and it is a little bit like that. So another maybe great example, which I'm very enthusiastic about, is work that I do with Taco Cohen and Maurice Weiler on. One was a PhD student, now full-time employee at Qualcomm, Taco Cohen, and then Maurice Weiler is now a PhD student at QValab. So QValab is actually a lab funded by Qualcomm at the University of Amsterdam.
Okay.
So that work is to include symmetries in deep learning. So in other words, if I turn my head, the objects that I see turn around in my brain. However, it's still the same objects, right? And so that's what we call a symmetry. If I move something, then it's still the same object, even though it has moved. And so incorporating these types of symmetries into neural networks is actually a very powerful way to make them better, turns out. And so with Taco Cohen, we started that process, almost, I don't know, 6 years ago or something like that.
Mm-hmm.
And it became quite successful. And now very recently, we did something that actually is quite, amazing, I would say. So we started to use the mathematics of general relativity, which is, the fundamental theory of gravity made by Einstein. And the same mathematics is actually in quantum field theory, which is, behind the standard model, which is the fundamental theory about particles. And this theory is called gauge theory. And it was actually the topic for my PhD thesis, which is interesting, I would say. So that came back after 20 years. And we started to incorporate these mathematical ideas into deep learning. And now we can do deep learning on arbitrary manifolds. So you can think of a sphere like the Earth, and you want to detect storms or other weather patterns on the Earth. Then you can use this particular tool, deep learning tool, to analyze these manifolds. You can also think about in VR, right, in virtual reality, you generate maybe a game or something like that. So you generate objects in your world. These are synthetic. And you can sort of put high resolution texture on these objects using this kind of tool. And so it's a very, very fundamental, academic exercise to take, these mathematical theories or that are used in theoretical physics and put them into a deep learning algorithm. But then actually once you're done and you look, at it from a distance, you discover all these beautiful applications actually. And that's, I think, the perfect line of thinking, right? So you start with something very fundamental, you make big progress, you make an impact on, a lot of, the whole field, and then you find that there is all sorts of interesting applications popping up that you hadn't thought about before.
Mm-hmm. And so some questions on that. You started out talking about the work that you were doing around symmetry, and then transitioned into the gauge networks. Are those? I didn't catch the relationship between those. Are those? Is that work specifically related? Did the one lead to the other?
Yeah, absolutely. So that's a good question because I went very fast over that. But and it follows precisely the same steps as were done in physics, right? I think in 1906 or so. Einstein came with his special theory of relativity, which basically described how different observers who move at a constant speed relative to each other see different phenomenon. And he and Maxwell found that basically magnetism will turn into electricity if you change observer and move it with a constant speed.
Mm-hmm.
So if a static observer sees an electric field, then a moving observer will see a magnetic field. And so that's a symmetry, right? It's a constant symmetry. It's like you rotate something, or you rotate the whole Earth around, or something like that.
Mm-hmm.
Now after that came Einstein generalized that into general relativity, and he said, well, actually, it's not just these global symmetries, but actually, we should be able to have a much larger set of symmetries, which is basically I should be able to, to change speed, and acceleration at any point in time, and I can sort of change my frame of reference differently at every point in space-time. And that's a much more general theory. It's called a local symmetry. So it's a much more general symmetry. It's called a local symmetry, and a local symmetry is also referred to as a gauge symmetry. And it turns out when you think about that kind of much larger set of symmetries, then he figured out, for instance, that acceleration and gravity are actually, the same phenomenon, but observed by, one person who is standing still and another person who is accelerating relative to the other person. And so now again, you'll have symmetries incorporated in your theory, and your theory becomes a lot richer. So that's happened. So exactly that progression has happened for us too. So we started with these global symmetries, and then we turned to local symmetries, and we went from basically doing deep learning on flat images to deep learning on curved manifolds.
Interesting. Yeah, when you first started talking about symmetries, the thing that came to mind was, that maybe you were going after the same type of problem as Geoffrey Hinton, who you've worked with, and his capsule networks. But it sounds like you ended up in very different places.
But I would say that you're actually quite right there. So it turns out that this is a little hard to explain, but out of this theory of symmetries, capsules emerge quite naturally. And it's a bit hard to explain how that precisely works. But it's true that what you'll have is these neurons. So when you apply translational invariance, these neurons will now be what we call feature maps, which is an entire sort of filtered image. And when you apply additional symmetries like rotation, you get sort of stacks of filter maps that sort of transform into each other if you rotate the underlying image. And that stack of filter maps is what we call a capsule. And that's actually what Geoff Hinton also talks about when he talks about capsules. Now he has this sort of dynamic routing algorithm, which is something on top of these capsules, which we haven't implemented in our code yet. But these two things are actually remarkably related. So you were actually quite right there.
So within the gauge CNNs, you have this concept of a capsule as well. Is that correct?
I would say yes, but it's also already in the sort of normal what we call group CNNs. So so before we did gauge CNNs with a local symmetry, capsules also naturally appear in these groups like a global rotation or a translation or something like that.
And beyond the conceptual, you've got this common conceptual foundation between Hinton's capsule networks and your gauge equivariant CNNs. Are there other relationships between the two that grow out of these, or what are the relationships between the two that kind of grow out of these kind of the shared feature maps and invariances within the networks?
Yeah, I think it would be a fairly technical discussion to try to explain that. But let me limit myself to saying that sort of in Geoff Hinton's theory, he basically says, okay, so I want my feature maps to be divided up in these capsules, and then basically the particular configuration within a capsule, is the pose of something, and then the strength of how much of that capsule is present, is what that indicates how strongly a particular object is seen in the image. So he goes in with sort of an intuition, and he builds it in. Where in our case we start with the symmetry from the principle of symmetry, and actually the math, basically drives us to these capsules. But in the end, they're actually completely the same thing. So I would say we laid a mathematical foundation for the capsules that Hinton's intuition sort of brought. And so he has dynamical routing, which is something that is sort of on top of it, which we don't do necessarily. We went into the direction of gauge equivariance, but it's we are basically in parallel, sort of developing these ideas, I would say.
Okay, and so is the idea with these gauge CNNs related to? Are they more compact, or do they open up new applications, or do they perform better? What does this approach buy us?
Right. So it's mostly if you want to do deep learning on something that's not a plane, right? So
the manifolds.
Yeah. So imagine you want to. So of course, a simple example is think of the Earth and think of a signal on the Earth, like maybe temperature or wind patterns or something like that, and you want to predict, maybe the weather in 10 days or something like that, or you want to find where is the storm or where is the weather pattern that you're interested in.
I also did a really interesting interview with a woman named Nina Milan, who does who does a Python package, geomstats, that is focused on doing statistics on manifolds. And the example that she gave was pretty interesting. It's like if you want to do statistics or learning on something like a human heart in medicine, it is much more naturally amenable to dealing with it as a set of manifolds or curves than in a typical rectilinear space.
Yes, so exactly. So that's on our to-do list, and we are actually collaborating with people who know much more about these medical applications than we do. But that's certainly one of the application areas. So you can think of a beating heart or something like that.
Mm-hmm.
Then you would put like a mesh on that beating heart, and you could sort of
a curved mesh as opposed to a straight mesh.
Well, the mesh has to live on the manifold, right? So there's a lot of nodes you distribute over this mesh, and you connect them by little lines, basically. Mm-hmm. And so then you can try to maybe predict whether this heart has strange behavior or something like that, as abnormal behavior, or you could try to figure out where certain pieces of the heart are. You want to segment them out or something like that. Maybe you want to detect where the vessels are, the valves are, something like that, right? So certainly, that's a prime example of where we have a manifold, and where we want to do deep learning on that manifold. And so that's certainly something that we're planning to do.
Okay, and so in talking about this mesh, you also bring up the idea, or it brings up for me the idea of like graphs. Is the gauge CNN kind of fundamentally a graph CNN, or is that something that you're working on as well?
You're asking really good questions, I would say. So, so in fact, one of the reasons why we are exploring this kind of meshed version of gauge CNNs, which is we put a mesh on the manifold and then we send messages between the nodes over the edges, is that it looks a lot like a graph convolution,
mm-hmm.
which is another object where you do deep learning on graphs. But a manifold, even a meshed manifold, is not a graph, because this has something to do with the fact that the neighbors are not sort of exchangeable. The neighbors are not a set. The neighbors are actually ordered. They something to the right has a different meaning than something to the left. And so people sometimes actually do graph convolutions on these meshes, but that's actually slightly suboptimal. And so the way we do it, so this gauge equivariant neural networks is precisely designed to do it optimally, in a way, to do it the right way. And we have a PhD student now at Qualcomm, who is Qualcomm, and PhD student at University of Amsterdam, Pim de Haan, who is precisely working on this topic. So he's precisely trying to nail this topic of, what is the difference between a graph convolution and this meshed gauge convolution, and, is there a real practical advantage above, doing it correctly in a mathematical sense? is there also a practical advantage of doing it in this particular way?
So all of these, we've talked about things from kind of very optimization-focused ideas like compression to Bayesian deep learning and gauge CNNs. Within Qualcomm, these are all more research-oriented topics as opposed to kind of product-oriented topics. Is that right?
Well, I would say that it's true to some degree, but I would say that compression, neural network compression, and quantization has immediate sort of practical applications. And in fact, the team of Time and Blankenvoort is already implementing these methods into a toolbox which is going to be commercialized. So, and the reason why this is important is that if I have my neural network that I'm very fond of, and I trained it in the cloud, maybe using TensorFlow or PyTorch or something like that, and now I want to run it on my phone, but it's too big to run on my phone because it takes too much energy, and then my phone doesn't have that much memory, right? So what I want to provide to the customer is a tool that automatically compiles this big neural network into a much smaller neural network that basically has the same performance as the bigger one. But runs on our Snapdragon sort of AI chipsets, very, very efficiently. Mm-hmm. And doing that is actually, you need to, get the neural network into a much more lean sort of framework, and then you also need to compile the operations that this neural network has to do, which is basically matrix multiplications, matrix vector multiplications. You have to compile them in such a way that they run very quickly on the particular piece of hardware. And you can also optimize that a lot. And so we are, for instance, also working on algorithms. So this is Chang-Yong Oh and Stratis Gavis, who are people at this QVA lab. We are working on what we call Bayesian optimization algorithms, which is algorithms which optimize over a very large discrete space, right, of choices. So the choices are, should I first, do this particular multiplication and then this addition, or should I first do it the other way around? So there is an exponential number of possible choices that you have there in optimizing that code. And so how can you quickly explore all of these possibilities? And so Chang-Yong developed a beautiful algorithm that with a minimal number of trials, quickly zooms in on the optimal sort of configuration of these discrete choices.
In order to apply a Bayesian optimization to this kind of problem, you first need to expose the features or the kind of the control levers, if you will, of the problem, which operation goes first versus second. Those aren't necessarily naturally exposed from the models. Is that right? Do you have to kind of do something or build something in order to be able to apply Bayesian optimization to these kinds of problems?
Yeah. So typically you can think of two levels. So let's say on a phone. So if I have a particular proposal of doing my computations, then I can, compile that onto the phone, the actual physical phone, and run it and measure how well I was doing. Now, of course, that takes some time, right? We are talking about, maybe seconds or something like that. I don't know, to actually measure, that configuration. And so, if you do it that way, you go very slow. But you can also build a simulator, right? And the simulator would basically figure out in approximation how good that particular configuration would be. But it's uncertain, right? And so you can imagine that you sort of, you first do a couple of steps of optimization on the simulator, which is very fast. And then when you get too uncertain, you then go to the physical device and you try a few things to see how well you're doing. You then update your simulator or that sort of surrogate model that estimates how well you're doing. And then you sort of keep optimizing there again. So there is this basically game that you play. You can measure things very precisely but quite expensively, or you can measure things very quickly but sort of approximately, right? And this is the choices that you have, and you have to navigate those choices as quickly as possible to get to the final best possible configuration.
One of the characteristics of dealing with devices that need to be produced in silicon is relatively long lead times as opposed to software products. Can you talk a little bit about productizing these types of ideas in that kind of environment?
Yeah, so I would say we mostly work on software, right? In many ways, what we do is can be quite quickly productized, I would say, because it's basically a software tool or an enhancement of some kind.
Okay.
But we do work with hardware folks, right? So we do work on exciting new hardware developments. For instance, compute in memory is something it's well known. It's a bunch of startup companies are also working on that.
Mm-hmm.
That's basically where you would, instead of moving that data that I talked to you about before from the DDR memory to the chip, you would basically do the computation directly in that memory cell. So you would directly do your computation in memory, which is actually analog. So this is actually volts and currents and stuff like that. And so now the game is, and that's a very interesting game. The game is you try to develop a piece of hardware that runs optimally for a particular algorithm, like a deep learning algorithm in this case. And at the same time, you're trying to adapt the deep learning algorithm to work as well as possible on that particular piece of hardware. And so this is a trend that you can see much more generally, which is that hardware design and software design are starting to become more and more integrated and entangled with each other. It's not just here, but it's in many other places where you can see that pieces of hardware are being replaced by pieces of software run on sort of a deep learning engine on a chip. You have in a heterogeneous compute environment with many different types of compute like DSP and CPU and GPU, etc. If you're faced with a certain computation, you will have to distribute that computation across all of these different compute engines. And you have to think smartly about how to do that, right? And again, there is a controller, sort of an intelligent agent that will have to learn how to do this efficiently. So you can see that software, machine learning, or learnable sort of software and hardware are going to get more and more tightly integrated, which I think is a very fascinating development.
Let's maybe shift gears and talk a little bit about kind of forward-looking ideas. You recently wrote a post about the kind of responding to a Rich Sutton blog. I'll let you maybe talk a little bit about the background and then the post, but it kind of ponders this idea of what's most important, models versus data versus compute. Can you talk a little bit about that work and how you see that kind of playing out in the future of the space?
Yeah, so I think this was more like my sort of rainy Sunday afternoon sort of write-up about something that I threw out there, and it actually got a lot of attention. So it was interesting. It sort of hit the right nerve. People are very interested in that kind of thing. And it's really about a super fundamental problem. And I think, researchers, we should talk about this more because it might determine for many young researchers in the field, where they want to head with their particular research. And so I was actually very grateful to Rich that he posted that particular post. He basically said something, and I may charge it a little bit, but it's like, we should really not try to model all that much because in the end, if we focus on scaling our architectures or sort of more general purpose machine learning architectures, if we wait long enough, then using Moore's law, you'll basically get to a point where you always get beaten by these kind of sort of scalable algorithms that are basically just eating data and turning them into predictions. And there's been a lot of examples that actually where this was actually the case, right? So we had we had models of speech where people had built models of the human voice tract, and they were sort of they were modeling how people produce speech, and then they were matching that with the actual observations, and then trying to figure out how the mouth actually moved, and therefore what word was being spoken. And later people found, well, if you just collect enough data, then you can just map, basically take the audio signal that hits your microphone, right, and map it, learn to map it to the words that produced it. And if you have enough of those pairs, like audio signal and word, then this sort of, in some sense, stupid, if you want, sort of a statistical tool vastly outperformed these kind of more mechanical tools.
Mm-hmm.
And this happened in speech, and it happened also in computer vision, where basically the best methods are now these deep learning methods, where you basically collect a huge amount of data on images, you segment them, you tell me what's the objects in the image, and then you train on all that data, and you get an algorithm that performs very, very well, better than anything else.
I mean, this all goes back to, I think, the most quoted example of this, and there are many, are the Peter Norvig unreasonable effectiveness of data paper, where he talks about Google. They're not better at this because they have better algorithms. It's because they just have more data.
Absolutely, right? So a lot of these internet companies are in the business of getting data. And by having all that data, they can do things that we didn't thought were possible before. And this was a very valuable lesson, right? So collecting more data and having the compute to do the computations is basically one of the reasons why we're seeing all this progress. But it begs the question: how far can we take it, right? This particular idea. And there's other people like Josh Tenenbaum who have been saying the opposite. So he's been saying, well, the world actually operates in the other direction, which means that physics, basically the data generating process is much more like we have objects in the world. These objects move under the laws of physics, or maybe the laws of psychology or sociology when we interact with each other. There's causal relationships, right? Things cause other things to happen. And then finally, signals hit our sensors, right? And that's what's being recorded. So that's the direction of, the physics of the world into the sensors. That's what we call the data generative model. And then deep learning does the opposite. It goes from these signals on the sensors and directly shortcuts a path to predict, what were the objects which were producing these signals. And actually, the brain, interestingly, does something similar, right? So we have in our brain the ability to simulate the world, right? I can close my eyes and I can imagine, what it means to ride on a horse or something like that, or to fall off a building, right? And I can just see it happen under the laws of physics. At the same time, I can also instantaneously recognize objects in the world. So there's these pathways in our brain which just take in sensory data and immediately segment the world into objects and sort of tell me what's in the world without me thinking about it. So in our brain, we have these two modalities as well. And Kahneman calls this slow and fast thinking, basically. So there's two quite different pathways to think. And so the question becomes, how far can we take this kind of data-driven approach? And my post was about, well, humans are a lot better in certain things than current algorithms. Algorithms have trouble with generalizing away from the domain in which they're trained, right? If I train an algorithm to play Go, and then I tell it, okay, now play chess, right? Or play Go on a smaller board even, or with different color stones or something, it gets confused because it wasn't trained for that.
Right.
For
the
humans,
example that always comes to mind for me was a video of in Peter Abil's lab training a robotic arm to, I think, untangle a rope. And it does great on a green, when the rope is on a green table, but when it's on a red table, and I'm making these colors up, but the idea is the same. When it's on a red table, it totally fails. It's just the models are that dependent on the specifics of the environment in which they're trained.
Yeah, and so and that's a very good example. And so maybe another example is I was driving on a road a couple of times, and then there was roadworks, and what they did was they kept all the white sort of lane dividers on the road, and they just put yellow ones, on completely different positions, and everybody knew what to do, even though the white lane dividers were still there.
Hmm.
And I'm pretty sure an algorithm, when it's not trained on that, will that get totally confused, right? And what's the underlying problem is that so they don't generalize because they don't understand the world in this generative data generating way. So what Josh Tenenbaum has been saying and many others have been saying is that you cannot collect nearly enough data to capture all of your corner cases, right? I mean, it's like there's so many things that can happen in the world. It's like an exponential number of things that can happen in the world, and many things are very rare. And so we need ways to generalize the lessons we learn in one context into sort of a completely different context. And one school of thought is that the only way to do that is to understand the world in a generative way. So and the reason is that the generative direction is much more efficient because it's modular. We have things that relatively independently do things, operate. These are the objects and the agents in the world, right? And they follow causal laws. They follow the laws of physics. And there's very few parameters in that, right? We know that the laws of physics eventually have very few parameters. And so that generative direction is a lot simpler than the opposite direction.
You said something really interesting in there, though. The entire phrase was understand the world in a generative way. When I think of most of the generative models that we're talking about, there's not any understanding there. It's just spitting out probabilistically the best next thing.
Yeah. So thinking about what it really means to understand something is a whole different area. But you could think about predicting the future, right? So let's say if I understand the world at some level, I can predict the future better, right? And now let's imagine I need to do some of a prediction, and I don't know the causal laws. If I know the laws of physics, and I know the laws of psychology, and I know what causes what, it's going to be far easier for me to predict the future than if I don't have all of that. In fact, I can train something in one context, and if I understand how physics work and I get into a completely different context, I can still predict the future, right? Because I understand the causal mechanisms. And so the claim is that the world is a lot simpler in the causal direction, or in the sort of physical sort of data generative direction, and is a lot more complicated in the opposite direction. Yet, if I define my application area narrowly enough, I can collect a huge amount of data on that particular narrowly defined problem. And then the inverse, going directly from the sensors back to the predicting the objects, is going to be more effective, right? Because that's the deep learning direction. So with sufficient data, that is the direction in which you actually also want to predict, which is the inverse direction from the generative model. And, that is the most effective way of doing things if you have a lot of data and you have defined your domain narrowly enough. And I think, therefore, we need to find sort of a middle ground. We basically have to say if we don't know much about a domain, if we get thrown into a new situation, we need to rely on our generative models of the world, and we need to invert those in order to make predictions. Yet, if we collect enough data in a certain domain, then we can form this direct pathway from the sensors directly to making predictions. And then that's going to be the most effective and accurate way of making predictions.
How do you take action on this idea, or how do we as a community of practitioners and researchers kind of take action on this idea?
Well, it depends a little bit on what you're interested in, right? So if you're interested in a narrow domain problem, like you want to predict speech, or you want to do speech translation or something like that, then you should go with the deep learning approach, right? Because that's just the best thing, because you can collect a lot of data and it works best. If you're interested in solving general AI, so developing sort of agents that are versatile and that can operate in many different circumstances, right? Then I think you may have to start thinking about integrating these two models. And so what we have been doing in the lab, in sort of my M lab at the university, is we have been taking a sort of somewhat older paradigm, which we call graphical models. So graphical models were models which were very popular like maybe 10 years ago or so, where you would take nodes in a
They seem to
graph,
be coming back a little bit, don't they?
maybe.
I hear a ton about graphical models nowadays. Like in recent NeurIPS, the past couple of years in NeurIPS, a lot of people seem to be doing work around graphical models.
Okay, well, it seems to stand to reason that something that is good eventually will find its way back when sort of the fire, the deep learning fire has burned out a little bit, and then of course you then get a phase where you can start to synthesize things, where you can say, okay, we had this in the past, we have now this, both are really good things. Let's see if we can sort of combine them a little bit. So this is some of the work that we're doing. So we have sort of a model where we will sort of generate, we have a generative model, let's say a Kalman filter, which is a dynamical model of somebody moving around in the world and sort of observing sort of things about the world. And in these graphical models, every node means something, right? That's the agent's position at every point in time is one node in this graph. And if you want to figure out, let's say, okay, if I have these sort of these partial observations about the world, like a bunch of images maybe taken from the agent, can I infer, where the agent was? And that you can do with something that we call inference. So that's a different inference than these days we call inference on a deep neural net. This is a probabilistic inference, where we basically say, what's the probability distribution of this person being at this position at this point in time, given all the observations I have right now. And so that's actually a message passing scheme. So you send messages over the edges of this graph to figure this out. That was belief propagation, and it was a very popular research topic, 10 years ago. Now we also have something. So the other option would be to collect a huge amount of data. Basically, person is here and observes this. If person is here, observes this, right? So if you collect a huge amount of data, you can also do it the opposite way. You can say, okay, map directly from my observations, back to the positions of this particular person, because I happen to have that data available. And if I have enough of that data, then I can actually do a better job typically than my Kalman filter, because my Kalman filter has like strong assumptions on linearity and Gaussianity, basically built in it. And if the world isn't linear, then you're in trouble, because you'll make wrong predictions. But if you just build this neural network, which goes in the opposite direction, takes the observations and directly maps onto the locations, then if you put enough parameters in it and you have enough data, then you can train it very, very accurately, right? So now the trick becomes, okay, so if I put into a new environment, I don't have data, so I will rely on this sort of clunky Kalman filter, but it will give me a fairly good estimate. And then as I go and collect more and more data, as I live in that environment, I'm going to train up the model in the opposite direction, and that at some point will become more accurate than my Kalman filter. And then I just basically switch to the deep learning sort of solution. And so this is one example where we have a message passing scheme on a graph that automatically switches between either the old-fashioned sort of inference and graphical model to the sort of more modern sort of graph convolutional neural networks.
Interesting. A lot of the folks that are pursuing deep learning as a path to AGI kind of ultimately feel like this thing that we call AGI, or maybe the step before AGI, will be an ensemble of perhaps many deep models as opposed to one single uber model. If you kind of apply that same thinking to what you're describing, you can envision an ensemble of many deep models and many generative models. And I'm almost thinking of like a hybrid car. If you've been in a Prius recently, you might have seen that little picture where they show you like whether it's the battery that's driving the motor or the motor that's kind of charging the battery, kind of this back and forth flow depending on what's happening and what the model is being, or the agent is being exposed to, that's determining, whether we're relying more on the deep model at any particular point in time, or the generative model? Is that kind of the way a way that you can see this evolving?
Yeah, so that's certainly the way I see this evolving. So let me stay with the example of a car, maybe. So you can actually, a modern car, even a self-driving car, would still have a whole bunch of rule sets to cover all the corner cases, because you can't collect enough data on these corner cases. But maybe in the future, there are enough, for a particular set of corner cases. Let's say, you're driving on freeways, you can do fine. You've collected a lot of data, but now you turn into Amsterdam, right? And there's so many exceptions and difficult situations where bicycles will crush you and pedestrians will do weird things and walk through red lights and all that, what's happening in Amsterdam. So you cannot rely on just a learned model, because it will fail, right? And so you have to basically go back to, if this, then that, if this, then that. And you have to know when to switch, right? And then maybe I can loop back to Bayesian statistics. So you have to understand when you don't understand, right? So this deep learning model or this machine learning model will basically have to figure out, okay, so I'm running out of my domain where I'm trained. I'm starting to fail here. I'm going to switch over to rules, or I'm going to switch over to the actual driver to make sure I don't get into an accident. And it's this interaction where, and then you can imagine where a lot of cars are slowly, getting into new situations, and they're all learning distributively, collectively. They're learning about some of these corner cases, and that gets embedded into the model, and then we slowly switch, to using that model.
And what's interesting to me about that example is that the premise seems to be that we will get to a point where the complexity of the environment is too much for the learned model, and then we need to switch to rules. But a lot of where learned models have proven themselves to be effective and powerful are these situations where we can't come up with the rules because the rules are too complex.
Yeah. So clearly, in many situations where you have enough data, you should not use rules because it's just not good enough, right? In fact, you should just train that mapping directly. But the advantage of rules is that you can express them in human language, right? I mean, we know in some sense when we're driving a car, right? We know, when to stop for a red light, when to, when somebody is, passing the street or something like that, or complicated combinations of situations. We know how to, express them in human language and turn them into a rule. I mean, there's going to be a gigantic number of rules. I think there's 100 million lines of codes in a car or something like that. So it's like huge. But, it is in some sense, a backup system for situations that you can't cover with your deep learning yet. And as I understand it, actually, when I heard a talk about this by Raquel Urtasun, actually, working for Uber, she mentioned that a large number of, a large fraction of the intelligence of a car is actually still rule-based. I'm sure they want to move more to deep learning, but it's still a pretty large fraction is still rule-based.
Awesome. Well, Max, this has been an amazing discussion. We could continue, I'm sure, for another hour, but I really appreciate you taking the time to jump on with us and to share a bit about what you're working on.
Thanks. It was a pleasure talking to you. Fantastic. Thank you very much.
All right, everyone, that's our show for today. If you like what you've heard here, please do us a huge favor and tell your friends about the show. And if you haven't already hit that subscribe button yourself, make sure you do so you don't miss any of the great episodes we've got in store for you. As always, thanks so much for listening, and catch you next time.